You know, when I first started working with digital electronics, I had resigned myself to the fact that all that exists is ones and zeros, highs and lows, nothing else. I knew that if you take those ones and zeros and organize them in unique ways, and you can create some pretty cool things like we've been doing so far. We're on a journey right now where we're creating a digital illumination system using nothing but digital electronics, and it's been fantastic. All of the different components that you can use in digital electronics, of course, make some pretty cool use of these ones and zeros. But until recently, I didn't realize that you can combine analog electronics into digital electronics. I have always thought that those two worlds shall never meet. Analog and digital are two very different things, but it turns out that the PIC microcontroller that we have been working on for the past number of episodes, although it's a digital component, it actually can interpret analog inputs. And we're going to make use of that today. But first, if you have not yet caught up on some of the previous episodes, I highly recommend you do that because for the last few episodes or so, we've been going through a little bit of a mini-series in programming a PIC microcontroller. We started right from the beginning, basics, and we've gone through a few of those episodes to where we are today. And if you haven't caught up, a lot of what we're going to be talking about today might be a tad confusing. So make sure you go back and see some of those before starting here. But if you've already caught up, well, let's jump right in. All right, now 2 episodes, we left our circuit looking something like this, where we had our PIC microcontroller here with a bunch of components. We had 4 LEDs that we were able to control, and we had this one switch. At that time, the microcontroller was set up to interpret the button presses and do various things with it. And then on the last episode, we expanded these 4 outputs that were leading to these 4 LEDs into this, where we took 3 of those 4 outputs to control 2 shift registers in order to get 16 LEDs plugged into that one microcontroller. But when we did that, that button was still plugged in and we didn't want it to interrupt any of the code that we built. So we disabled that button by commenting out a couple of lines in the initialization sequence and also by preventing one of the interrupts from firing. But now we want to start using that button again. So we're going to re-enable some of those things we disabled last time. So first we're going to re-enable the CCP1 interrupt along with the timer 1 and serial port 1 interrupts. And then we'll uncomment these 2 lines. So now the microcontroller will be able to recognize the button press. We need to make sure that it does the right thing. So scrolling up to the CCP1 handler, we can see here that we're directly manipulating latch C bits. And this will be a problem because in the previous episode, we used the exact same bits as an SPI communications channel so we can control the 16 LEDs. So if we manipulate this directly, we're going to mess up that communication. So I need to remove that line. And instead, we want to set the illumination intensity to minimum by sending a 0 on the serial port communication channel. In case you've forgotten, what's happening in this part of the code is we're determining the action of what happens when you hold the button down for at least 2 seconds. And so what we've just told our microcontroller to do is when it detects that the button has been held down for at least 2 seconds and then released, the intensity should be set to minimum. And now I'm going to adjust my branch offsets to accommodate the new code that I put in. Let's go through the code of this handler just one more time so we can realign with what's actually happening here. This handler gets called whenever the microcontroller detects a button press. After clearing the action flag, we disable the capture and compare module to prepare for a change in mode. Then we increment the value in a register that we're calling the button state. Then we test what button state we were in, and then branch forward if the button press was just detected. In which case, we're going to jump to this line of code, where we adjust the speed of timer 1, and then re-enable the CCP in compare set mode. By slowing down the timer, we can wait the full 2 seconds while the button is pressed. And if the button stays pressed for 2 seconds, then this handler is triggered again. But this time when we do the test, it does not branch forward and instead goes to this line, which we just adjusted to set the intensity to minimum. Now there is one more place where we need to make an adjustment, and that's when we detect the button release. So first we're going to remove the 2 lines that directly manipulate latch C and replace it with code that sends the current intensity over the serial communications channel. Now we can assemble and program. Now let's see what happens when we push the button. Yep, it jumped right to the maximum intensity, and if we hold the button, we should see it go back to minimum. And sure enough, it does. Oh, wait a minute. When we release the button, it appears to jump right back to the maximum again. Oh, we can fix that pretty easily. All we need to do is test the button state whenever the button is released, and if we know that we held it down for the minimum 2 seconds, then we skip the line of code that sets the intensity to maximum. So in our release button handler, we want to remove the clear button state line from here, and instead, we want to put it over here. Then, just before we set that maximum intensity, we'll apply a test. And in the case where it was not held, we're going to proceed to set the intensity to maximum. But in the case where it was held, we're going to branch forward and simply clear the button state. And let's see if this works. Yes, it does. So now we're ready to interpret this button signal a little bit closer. Let's take a look at it on the scope. We're looking at the microcontroller input that the button is connected to, and at rest we can see it's sitting at about 3 volts. Yeah, I know. I see a little bit of noise on that line as well. I'm just going to blame it on the breadboards. And when I press the button, it drops right down to almost 0, which is precisely what we'd expect. And if I tap the button repeatedly, you'll see it go up and down, but you might also be seeing some interesting things happen on that waveform. It's not exactly up and down, there's a bit of a gradual change there. Now if we zoom in and freeze it on one of those button presses, we can take a better look. There, we've captured one of those button presses. And zooming in on this, we can see that it takes about 5 milliseconds for that signal to drop down to 0. And that's due to the resistor and capacitor over here in that circuit, which softens the change. Now that was very deliberate because we wanted to debounce this button or prevent rapid changes to accommodate for any sort of hardware deficiencies in the switch. So we're not going to be covering debouncing in this episode. What's important to note is that it takes time for it to settle at the new voltage. And on the scope, we can see that that voltage is nearly 0. But it doesn't have to be 0. I could change that voltage by adding a resistor into the circuit, such as right over here. So let's take this 10 kilo ohm resistor and insert it between the button and ground. Now when we press the button, we can see that the voltage doesn't reach 0. It reaches somewhere around 580 millivolts. Okay, that makes sense. When we close the button, this has become a voltage divider. And we can see that by looking at our circuit. With this switch closed, the voltage at this point over here will be divided between this 47 kilo ohm resistor and our new 10 kilo ohm resistor. Here's what the math looks like to figure that out. R out in this case is our new 10 kilo ohm resistor down here, and R in is our 47 kilo ohm resistor up there. Plugging in those values, we get a ratio of 0.175. And solving for V out when V in equals 3.3 volts, we'll get a result of 579 millivolts. Now this is neither a high or a low. Our digital high level in this circuit is 3.3 volts. That's the supply voltage that we're feeding this circuit. And the digital low is 0 volts. So this is not quite either. And yet, when we push the button, the digital microcontroller still interprets that as a low. Now, if we dig into the electrical specifications section in the datasheet, there's some information here about the specification of those input and output ports. It tells us that our microcontroller will register a digital 0 if the input voltage is at maximum any of these values over here. And the one that matters to us is this one right here with the Schmidt trigger buffer at 0.2 VDD. Now, in case you're wondering, that's the default setting for this particular PIC microcontroller. It sets the input levels using the Schmidt trigger buffer. It does not use the TTL buffer. Although we can change it, we never did. So that means for us, any voltage level that's less than 0.2 VDD would be registered as a digital low. And since our VDD is 3.3 volts, that means anything less than a 0.66 volts or 660 millivolts will be registered as a 0. And since our button brought this signal down to about 580 millivolts, our microcontroller currently can't tell the difference between 580 millivolts and 0, so it thinks it's a 0. So now for fun, we can try changing this resistor to something else, but instead of doing that, why don't we add a second switch with a different resistor? In this case, it'll be a 4.7 kilo ohm resistor. And take a look at the signal as we press it. Oh, look at that. With the 4.7 kilo ohm resistor, it's settling at around 330 millivolts. And yet our digital microcontroller still can't tell the difference between these two buttons. Now for completeness, we'll add one more button into this circuit, but we'll make use of this rotary encoder that we have here because it also has a push button feature. It's hard to see on the camera, but this rotary encoder over here also has a switch that can be pressed, and these two white leads coming off the end here are the signals for that switch. But we will not include a resistor, so this will always bring our signal down to 0. And we can see when we push any one of those 3 buttons, the effect is exactly the same, even though the actual signal level is very different. The microcontroller doesn't know the difference because all 3 of those signals are below 0.2 VDD, so it thinks it's a 0. But as you might expect, this microcontroller does have the ability to tell the difference, and that's using the analog to digital converter. So to get this peripheral working, there's a few things we have to configure first. And one of those things is this thing called a charge pump. Now, I'm not going to pretend to know all the details as to why this is useful. In fact, I'm not even sure that we have to enable this because I tried doing this without the charge pump and it worked fine. But based on what I read in the manual, it suggests to use this thing whenever our input voltage is not 5 volts. And since we're running on 3.3 volts, it suggests to use it. So I did. And the manual really doesn't contain a lot of detail as to why you'd want to use the charge pump. It basically just describes the different settings that you have. So like, whatever, we'll enable it. So to do that, we'll go into our initialization script and maybe right around here. Yeah, this looks good. We'll put in the code to enable the charge pump. And that value you can see here is 11 for bits 6 and 7 of this register. There's also a charge pump ready status register over here, which will let us know when the charge pump has reached a steady state operation. Okay, so presumably that means I need to turn it on and then wait for an acknowledgement that it's been turned on. Of course, I don't know how long that'll take. So in the code, I'm going to continually want to reset the watchdog timer as we wait for this. Now, we covered what a watchdog timer is in one of the previous episodes. If you've forgotten, make sure you review it. It's not critically important for what we're doing here, but it's really helpful to know what that watchdog timer does. Now that we've enabled the charge pump, we can get to configuring the analog to digital converter. And one of the first things we need to do is tell the device which pin we're going to be detecting analog voltage on. Now we already know which pin that is. This is RA2, the pin that the button is connected to. Now in the manual, there is this little importance section that basically describes that when you're changing the channel, you got to do a little bit of a song and dance to discharge some internal capacitor or whatnot. So let's put the code in to do this song and dance in the initialization sequence. And it looks a little bit like this, where we prepare to enable the ADC on channel VSS. We run a conversion and then we wait for that conversion to complete, which is why we need to put this clear watchdog line in here. And then once it is complete, we can then disable the ADC and set it to channel RA2. Now, after all that, the analog to digital converter should now be set to monitor our button input. There's one other important configuration we need to make, and that's for the conversion clock. For this analog to digital converter to actually make those conversions, it takes time to do what it does, and we can control how long it takes. In here, there's a chart that says the minimum amount of time it can take is 62.5 nanoseconds, all the way up to 64 microseconds. Now you'd think it'd be pretty straightforward to just choose the fastest time and be done with it, but it doesn't work that way. There are some times that are actually too fast for the ADC to do what it does. It doesn't apparently give it enough time to settle on a proper value, and so the value you get will be inaccurate. There's also, you can also choose times that are too long for this thing to work, and apparently those are also not accurate. You have to choose a magic window, and it's all dependent on the speed of your processor or how fast it's running. So it makes it a little bit complicated. Now there is an easy button here. There is a specialized ADC clock which runs at an internal rate separate from the main system clock, and it takes somewhere between 1 and 6 microseconds to do what it does. So we're going to choose that one to keep things simple. And that setting is right over here, ADCRC. So just before we change the channel, we're going to set the ADC conversion clock to ADCRC. Okay, so now the ADC should be configured, but we need to be careful as to when we start that measurement, because remember, the button signal takes time to settle. Here's a little diagram that I drew that shows the signal drop when a button is pressed. On the vertical axis we have voltage, on horizontal axis we have time. You can see here at TR or time R, the button is pressed and the signal begins to drop. And it's critical to understand that the microcontroller won't know when the button was actually pressed. It has to wait for the signal to drop below 0.2 VDD, and that takes some time until right over here. This is TD when it's actually detected. Only then does the microcontroller recognize that it was pressed and actually calls the handler to do stuff. But notice the signal has not settled yet. It takes a little bit more time for it to settle, and I'm calling that TS. So what this means is that we cannot test the voltage on the pin as soon as we detect the button press. We have to wait some time for that signal to settle. How long? Well, lucky for us, we can calculate how long we need to wait. There's a wonderful Wikipedia page on what an RC circuit is. Remember, we have an RC circuit. That's this capacitor and this resistor over here, which cause this gradual change of the signal. And according to physics, it takes about 5 time constants until we can assume that the signal is settled. And the time constant is basically resistor times capacitor. And so for us, that resistor is 47 kiloohms and that capacitor is 22 nanofarads. If you do the math, that works out to 5.17 milliseconds. So the time between TR and TS must be at least 5.17 milliseconds. We don't actually know the time at TD because this will vary depending on the final settling voltage of the signal. So assuming TD starts over here somewhere, as long as we wait at least 5.17 milliseconds from the moment the signal is detected, we should be in good shape. So now we can make some changes to the code, and the first thing we need to adjust is our button states. Right now we have 3 button states. We have 0, which indicates a button's released, 1, which indicates it's pressed, and 2, which indicates it's held. On our chart, we start at button state 0 and then transition to 1 at the point TD. And then we transition to 2 at the point TH, when we recognize that it's been held for a certain amount of time. So we need to insert another button state that allows us to wait until our signal is settled. So we still want button state 0 up until TD, at which point it'll transition to button state 1, which we're going to call wait. And then at TS, we want it to transition to button state 2, which will now become pressed. And then at TH, we will transition to button state 3, which is held. So let's make that change in the comment first. Then in the handler, we'll adjust the comments for our first test. Although the code hasn't changed, we're now testing if the button state is 2 or 3, and we're going to skip the next line if it's set, which means that the button is pressed or held. Now, if it was neither of those, we're going to branch forward a little bit because we want to wait for the button to settle. We don't know how much we're going to branch forward yet, so we're going to leave that part blank. Now, in the case that the button state was 2 or 3, we now need to do another test to figure out, well, which one was it? And if it was set, we now know that the button was held. But if it was not, that means it was button state 2, in which case we're going to branch forward to somewhere because we've pressed the button and are continuing waiting for the hold. And only in that state can we initiate the analog to digital conversion. Now we can fill in the missing branch values. So if we're waiting for the voltage to settle, we want to branch forward to this line over here, which in this case would be F. When the button state is 2, we're pressed and continuing waiting for a hold, we want to branch forward to this line over here. So the offset is 7. And we need to adjust this branch because we want to make sure we still end up in the right spot, which is right over here before the subroutine ends. Let's not forget to change the test in the button release handler as well. Right now we're testing if the button state is greater than 1 and skip if clear, but what we actually want to do is test if the button state is 1 or 3 and skip if clear. So what we've just done is we've inserted a new button state after TD and before TS, right here on our chart. And we know exactly how long that's going to take. It's going to take 1 full cycle of timer 1, which in this case is 65 milliseconds. And that's plenty longer than 5.17 milliseconds, which is necessary. But we're kind of dependent on timer 1 because if you remember from 2 episodes ago, the entire button press algorithm makes use of the capture, compare, and PWM module, which is very dependent on timer 1. And because timer 1 is a 16-bit timer, we have to wait for the whole 16-bit timer to overflow to recognize that something has happened. There's one more little bit of code that I want to insert, and that is to test that the analog and digital conversion has completed before we set the new value. I don't think it's likely, because based on what we've been working with, that should take somewhere between 1 and 6 microseconds, but I don't know. I'm going to put it in there anyways. It'll probably never get triggered, but better safe. Assemble and program. So now the buttons still work as expected. Now you may notice that a quick press sometimes isn't recognized by the controller. That's because it takes 65 milliseconds for it to detect the press, which is actually a little bit of a long time. I mean, we could leave things alone. It's really not that long of a time, but we can improve things a bit. Now, remember earlier I said that the timer 1 is kind of fixed. We can't adjust our timer 1 speed. Well, we kind of can, but in order to do that, we need to change the entire system speed. See, here's all the possible settings for timer 1, and currently it's set to the SF internal oscillator, which in this case is 1 megahertz. The only other options we have are slower at 500 kilohertz or 32 kilohertz. We can also set it to the instruction clock, FOSC over 4. For us, our system clock is currently set at 4 megahertz, and so the instruction clock is a fourth of that, which works out to 1 megahertz. But if we increase the system frequency to, let's say, 8 megahertz, and then set the timer 1 clock to the instruction clock, well, now our timer 1 will be running at 2 megahertz, which should double the timer 1 speed, which means our delay will be cut in half to about 33 milliseconds, which is probably more user-friendly. So let's make that change. Instead of configuring the timer 1 fast clock speed to SF1 megahertz, we'll set it to the instruction clock. Then in the initialization code, we'll set our system clock to 8 megahertz. Let's make sure we adjust our comments to reflect this change. And we can see right there that the timer 1 cycle should now take 33 milliseconds. And it looks like I actually forgot to include the timer 1 slow speed in here. Remember, we had originally configured that to 2 seconds. Okay, let's assemble and program this change. Now right away we can see the faster blinking LEDs. I don't know if it's capturing this on camera, but that confirms that our system is running way faster. And pushing the button still results in what we expect, and a nice rapid push is still captured. So now our analog to digital converter should be working, but we're not actually doing anything with the results, which is why we're not seeing any change. So I guess in order for us to see the results, we could temporarily output the actual value that comes out of the ADC to our LED display, just to see what value it's interpreting. But before we do that, we're going to have to tidy up a little bit of our code. I'll show you what I mean. So the way our code works right now is every time we send a value to the indicator, we have to do all this prep in the button press handler. We do it again here in the button release handler, yet again in the rotary encoder handler, and one more time in the initialization sequence. So we can clean all this up by packaging all of that code up into a subroutine and then calling the subroutine whenever we want to change the indicator value. So right over here, before our initialization sequence, let's add in a new subroutine called indication that prepares everything once before sending it off to the serial communications device. Then we can go back to wherever we're changing the indicator value and simply replace all of this with one line that calls our new subroutine. Now don't forget, whenever we remove lines of code, we have to adjust our branch statements. Let's do it again in the button release handler, adjust our branch statements here too. Then in the rotary encoder handler, no branch statements here to adjust. And finally in the initialization sequence. Now let's test it to make sure that everything still works the way we expect it to. And sure enough, it does. Now we can adjust the code such that whenever we release the button, we can temporarily send the output of the ADC peripheral to our LED display. So right over here, I'm just going to comment out a few of these lines that send the maximum intensity. And instead, I'm going to capture the high byte of the ADC output to the working register and send it directly to the serial buffer so we can see the output. Now the reason we're only collecting the high byte of the ADC output is because we're ignoring the lower byte. Now I didn't get into this earlier, but the analog to digital converter on this particular microcontroller is actually a 10-bit converter. We can configure the output such that it's left aligned or right aligned for various different reasons. Now, like I said, I skipped over it, but we configured the output, or I think we left it at the default to be left aligned, which means that the high byte will have the highest 8 bits bits of the actual reading. The lower 2 bits and the rest of it is completely ignored. Now, because the ADC has some error built into it, those lower bits are kind of unreliable anyways. And so it's okay that we only took the high byte. And as we're about to see, even some of the lower bits on the high byte might be unreliable. Well, let's take a look. So after we assemble and program, you're going to notice that when we push a button, we actually get some interesting values on our display. If I push a different button, we'll see some different values. Now, the first thing we got to remember is because we're doing this temporarily, we didn't really do it properly. We have a 16-bit display, but we're only sending an 8-bit output. So really, we should only be paying attention to the first 8 bits of our display and ignoring the higher 8 bits. Which means these 8 bits over here, we just need to ignore them and only look at the lower bits here. So if I push this button, the result that shows up looks to be, well, that's a 2-9. So this is hexadecimal 2-9. If I press this button over here, we get a different result. This is hexadecimal 1-4. And if I push this button, it's hexadecimal 0. So that proves that the ADC is giving different results for different readings. Now you recall earlier when I said that the lower bits are unreliable, and if I push this long enough, you might see that I get a different result sometimes. So usually I'm getting the result of 2-9, hexadecimal 2-9, but every now and then I see, oh, there it was, hexadecimal 2-8 showed up. The same thing happens with this button. Normally, I'm going to get a result of 1-4, but sometimes I get a result of 1-5 every now and then. Remember, the analog to digital conversion is doing the conversion every single time, and there is some error inherent in that. And there's also error inherent in my circuit. I mean, look at this. This is just a mess of wires on breadboards. So I would have to expect that there is going to be some irregularities there. Hence, sometimes we get one result and a few times we get another result. So in our code, when we interpret those results, we have to acknowledge the fact that we're not always going to get exactly the number that we expect. Now, there's a few different ways we can deal with this, and I'm going to show you 2. Now to illustrate this, we're going to use a spreadsheet. The first column basically counts from 0 all the way to 255, representing an 8-bit output from our ADC high byte. The second column is simply the hexadecimal version of that decimal number. So it goes from 00 to FF. Now remember the values that showed up when we pushed the button. Switch 1 usually gave us the result of 2-9. Sometimes 2-8. And switch 2 usually gave us 1-4, sometimes 1-5. Switch 0 always gives 0. So in our spreadsheet, I wanted to put those values in. Here's switch 0 that aligns with the ADC output 0. Here's switch 2 that aligns with the ADC output 1-4. And here's switch 1 that aligns with the ADC output 2-8. Now, recognizing that it's not always 2-8 or 1-4, sometimes it's 2-9 or 1-5, or it might even go the other way depending on different environmental factors. I want to create what I'm calling a landing zone within this spreadsheet. So if I look at all the values that can occur between switch 0 and switch 2 and pick the midpoint, I'm going to define the upper half of this as the landing zone for switch 0 and the lower half of this as the landing zone for switch 2. And I can do the same with the difference between switch 2 and switch 1. I'll define the lower half of this switch 2 landing zone as switch 2 and the upper half of this landing zone as switch 1, split somewhere in the middle. And then the lower bit of the landing zone for switch 1 will go all the way down to the end. I just recognized that I had switch 3 indicated in my Excel spreadsheet, but yeah, you know what I'm trying to say. Now that we've defined these landing zones in that spreadsheet, I'm going to use the output of the ADC as a memory address, and I'm going to ask the code to go to whatever that memory address is. Now that memory address should line up with the landing zone that we created, plus or minus a little bit. That's why we've given it that zone. So if the ADC comes back with a value that's 1 or 2, or in our case, maybe even 4 off of where it should be, it's still going to go to where that landing zone has been defined in memory. Let's do it in code and you'll see what I'm talking about. Going back to the button release handler, these lines that we commented out were originally to set the intensity to maximum. So since we're not doing that anymore, we can actually just remove those commented lines. We can also remove these 3 lines which send the output to the serial buffer, because instead of sending it to the serial buffer, we want to do something else with the output of the ADC. First, I'm going to set the program page to 7 using this new movlp command. Then I'm going to use this CALLW command. So all CALLW does is it takes the value in the working register and it assumes it's an address. And by calling it, I'm going to that address in memory. But because I set the program page to 7, the memory address that it's going to is somewhere far, far away. If you look in the datasheet under the memory organization section, you can see where the on-chip program memory is located. It starts roughly at 005 hexadecimal and goes all the way to 7FF. Now that's specific to this particular chip. You may have a chip with bigger or smaller memory, in which case you might want to use a different program page. Scrolling down a little bit in the same section, we can find a little bit more information about how that CALLW actually works. The 8 bits that are located in the W register are used as the lower 8 bits of the address. The upper 7 bits of the address come from this funny place called PC lath, which means we have to set the PC lath register before calling the CALLW instruction. And that's precisely what movlp does. It sets the PC lath register to, in this case, 7. And we can, going back to this diagram, we can see that 7 is the last 255 bytes of the on-chip program memory. So we're telling it to go all the way to the end of the memory bank to find something. But of course, right now it's not going to find anything. We need to put something there for it to find. And to do that, if we go right to the bottom of our code just before we hit the end instruction and insert org 0700, this is telling the compiler that any lines of code that I put after this will be written to the program memory at address 700. And this spreadsheet is what I want to put there. Now, of course, we can't copy the spreadsheet exactly into the code. That's not going to make any sense. But we can do this. We can fill these lines with branches that all point to specific locations. All of the branch lines over here pertain to a landing zone for switch 0. And I want all of them to send the code to this line over here, where I'm going to return the intensity value of switch 0. And in this case, it's going to be 0F. That value is going to be returned in the working register when we drop back out of this subroutine. And the next few lines of code are more branches which all point to this line over here, which returns a 03, which is the 20% intensity and aligns with switch 1. Keep going and you can see the final landing zone is gigantic. It actually fills the rest of the 700 memory block, and right at the end, we have a return LW instruction for a 60% intensity, and that's going to be 09. So yeah, we're using an entire memory block, in this case 256 blocks of memory, to return 3 possible options. It seems a tad inefficient, and it kinda is, but our trade-off here is program memory for speed. If you think about what's actually happening here, we're using the output of the ADC as an address. It goes to that address, returns a value back to the main program, and it does so in a very short amount of time. But it's doing so using a relatively large area of program memory to figure it out. This is known as a table lookup, and it's incredibly fast, it's incredibly efficient in speed, not so efficient in the use of memory space. But if you have lots of program memory, this is a pretty cool way, I think, of making use of that program memory. So I'm going to insert a comment that basically says, this is our button lookup. And then going back to where we make that lookup, we've got to remember to return the program page back to 0. Now that we've retrieved our value from the lookup, I'm going to move it to a register that we've already defined as a target intensity, and then call our indication subroutine to send it out to the indicator. And don't forget, because we've made some changes to the code, check the branch statements and adjust as necessary. Let's assemble and program. Now look at that. You can see all the extra code that we're writing to our program memory from address 700 to 7FF. And it also becomes apparent to see how much space we actually have available. Currently, our code is only going to 15F, and we have everything between 15F and 700 as empty space, so feel free to fill it with lookup tables. Now let's see how it works. Pushing switch 0, look at that, goes right to position 9 every single time. This will be extremely reliable because of those landing zones. It will always get position 9. Switch 2, yep, position 3, every single time. It's always going to get position 3. And switch 0 is always going to get maximum intensity. Using a lookup table in this way has some awesome advantages. You saw that regardless how many times I pushed the button, the results were reliable. That's because we're using relatively big landing zones to force a single output. And depending on how big those landing zones are, the margin for error is wide. Now, we only have 3 buttons in our setup, which means we could put more buttons in our setup and use more of the available space, but then each landing zone gets smaller and smaller and smaller, which can introduce the possibility of errors. Nonetheless, in practice, we saw that the ADC output for the high 8 bits only resulted in the lowest bit being different. So that means that our landing zones currently are huge, and we can easily make them smaller, which means we can add more buttons. So it's pretty cool that we can add more buttons using this same technique and get very reliable results. The disadvantage, though, is that if we ever wanted to change the output, we have to change the code. So right now, this button always results in a value of 9, and this button always results in a value of 3. If we wanted to change that to, let's say, 2 and 10, for example, that necessitates a code change. We could use this lookup table in a slightly different way, such that we don't have to make a code change if we want to get a different output value. So here's a similar spreadsheet in which the first column is the same as the last spreadsheet. We count basically from 0 to 255. The second column is also the same as the last spreadsheet, where we identify the same number, but this time in hexadecimal. Now, in the next column, what I've done is I've said % of V in. What we're trying to do here is describe the output of the analog to digital conversion process of the reading at that input pin relative to the system voltage. So for example, if the ADC output is 0, that means the reading is 0% of the system voltage. If the ADC output is FF, then the voltage is 100% of the system voltage. And everything in between. These numbers are simply just a calculation we put into the spreadsheet. Now remember earlier when we talked about how this microcontroller can actually recognize the button press? It still is a digital system, and therefore it still needs to recognize that the button was pressed, which means that the voltage must drop to 0.2 VD or below. So that's why I've called the next column valid range, and I've basically set it to true as long as the % V in is less than 0.2. So what this really means is although we have 255 possible places to identify landing zones, the ones that are really only relevant are a small portion of them, 20% of them to be exact. And that 20% must fall between the ADC output 00 and ADC output 32 in hexadecimal. So technically we could get around this limitation and open up the landing zones to the entirety of the 255 slots, but that would require some significant code changes because remember, our code still depends on the digital domain to detect the button press. By necessity, it has to wait until the voltage drops below 0.2 VDD, and then it says, aha, I've registered a 0, therefore the button has been pressed. Only then do we test the actual voltage. If we wanted to test the full range, the only way to do so is to continually test the voltage at the button. So we'd have to set up a whole other system to pull the voltage and test it. And every time we test it, we have to check to see if the button was depressed. So we can certainly do that, and it's a little bit more complicated. Based on our requirement right now of only having 3 buttons, the existing space, which is only 20% of the full 255, is still plenty big enough to accommodate this. So just know that if you did want to use up more space for more buttons perhaps, or more larger landing zones, you could do that, but it would require a much more significant change, and we're not going to do that today. So for now, let's assume that we are limited to the 20% range that we have in a spreadsheet. So once we know how much of that range is valid, now we can start performing some calculations. And those calculations need to come with the resistors that we have in place here. So we have the Rin resistor, which is this one right over here in our schematic, 47 kilo ohms. And then we have our out resistor, which is this one in our schematic. And right now we have it set up for either 10 or 4.7 kilo ohms. But over here I've indicated a range between 0 and 11,463. If you're wondering what that math is, it's basically just the voltage divider calculation we ran into earlier. But instead of using the 10 kilo ohms as fixed values for R out, I used the spreadsheet to figure out what those values would be for a V out and V in ratio between 0 and 0.2. The result is these values that you see here that fall within the indicator range of 100% and 2%. And that worked out to roughly 50 possible outputs of the ADC. Our indicator, after all, is only 16 bits. So we take the 50 possible outputs and divide them up amongst the 16 potential indicator outputs. And through a little bit of spreadsheet rounding, I ended up with these values over here, which are translated into hexadecimal in this column. So what all this means is that if our ADC outputs a 0 or a 1, I want my indicator output to be F. If our ADC outputs 2, 3, 4, or 5, I want our indicator output to read E. If the ADC output is 6, 7, or 8, then I want the indicator output to be D. And so on, all the way down to an indicator output of 1, which would happen if our ADC output was 2E, 2F, 30, or 31. Notice I am skipping 0, even though it's here on the sheet, because right now the way our code works, the only way to get an intensity level of 0 is to do a long press on any one of the buttons. It's not going to stay that way long term, but for now that's what we got. So now we have to make a lookup table out of this. And although this looks a little complicated, I totally understand that it does. The actual code to make this reality isn't. The only thing we need to do is change what we have right now for a lookup table into this. So regardless as to where you land in the lookup table, you'll always encounter a return LW instruction. And the value that it will return is going to be the same values that we saw in our spreadsheet, in order. You can see how we have 2 Fs, and then we have 4 Es and 3 Ds, and then another 3 Cs. It's the same in our spreadsheet, 2 Fs, 4 Es, 3 Ds, 3 Cs. In the code, I've put some comments to kind of help keep track as to which number we are. Also, I've included the intensity percentage, which should show up, and the associated resistor value. So there's the hint. It's the resistor value which determines what the output will be. Currently, the resistors that we have in there are about 10K, so we should get an output of 2 for the 10K resistor button. And the 4.7K resistor button, we should get an output of 8. Let's try it out. This is the 10 kilo ohm resistor connected to this button. So if we push this button, we should see the 2 light up. So that's 0, 1, and 2. When we push it, oh, it's 3, actually. So this is giving a result of 3. Okay, that's kind of close. Our lookup table suggests that 3 should only happen for a resistor value between 8.7K and 9.2K. Okay, let's try the 4.7 kilo ohm button. That should give us a value of 8. That's this one over here. Push that, and oh, that's actually 9. And based on our lookup table, that should be somewhere between 3.7 and 4.4 kilo ohms. Okay, so clearly it's not perfect. Remember, we're working with breadboards over here, which are notorious for current leakage, particularly if you're working with very high resistance values like we are, 47 kilo ohms and 10 kilo ohms. That results in very low currents, which tend to find other ways to get to ground through these breadboards. So the voltages that we're reading are probably lower than they should be, which results in the errors. Now, I did do some testing, and I did confirm that we do have some voltage leakage out of these breadboards. we could fix that. A, by putting this on a proper printed circuit board. That's one way which we could fix it. The other way we could fix it is by increasing the currents, by reducing the resistors that we're using. But that has a couple of drawbacks. If we reduce the resistors, that pulls a little bit more current, which exposes the switches to more current, which eventually exposes them to more sparking every time you push the buttons, which reduces their life expectancy. The other thing that it also introduces is you probably figured out the way to actually change these outputs is to change the resistor values. And if we use lower resistors, then it is actually quite tough to find resistors with high precision that would work in this scenario. But that is one of the ways that we can change the values of this. In fact, that's one of the advantages of this system, even though clearly it has some disadvantages of accuracy. The advantage here is that I can change the output simply by changing the resistor. See here, this was the 10 kilo ohm button, which results in an output of 3. If I simply take a 20 kilo ohm resistor and put this in parallel, it's going to change the result. Look at that. It went to 7. If you perform the calculation, a 10 kilo ohm resistor in parallel with a 20 kilo ohm resistor should result in a total resistance of about 6.7 kilo ohms. And using our table, that should result in a value of 6. We got 7. It's a little off, but we already know why. In principle, the system works. Previously, we used a lookup table where we were able to get very specific results using that landing zone idea. This time, we just changed the way that we're organizing that lookup table, and the end result is that we actually get a little bit less specificity on the output, but we're able to accommodate a range of inputs, and all we really need to do is change the resistor. We don't need to change the code. And so that is pretty powerful by itself. Depending on which method you prefer, well, you can choose either one. I think they're both awesome, and with some better equipment and not putting this on breadboards, we'd probably get some much more accurate results even by using this method. So look at that. We now have this 16-bit digital system that's responding to rotary encoder inputs, 3 separate buttons which set different intensities, also responding to long presses on those buttons to bring that intensity down to 0. I think we've done pretty good because all these inputs, well, the button inputs anyways, not the rotary encoder, are connected to a single pin on this microcontroller. And we were able to determine which button was pressed simply by assigning a different resistor to each button and then leveraging this analog to digital conversion peripheral on this PIC microcontroller. And it's all done using a single pin. That is incredible. I'm so happy that these digital components have analog capabilities, or else we wouldn't have been able to make use of this. Now, you've probably noticed that our intensity changes rather abruptly. It goes from one intensity level to another instantly. There's no smoothness to the change. Well, that's what we're going to address on the next episode. We're going to figure out how to make these changes smoothly. Until then.